Welcome all. Now I am going to discuss question number 23 from the GATE 2018 paper Electrical Engineering. The question is, the waveform of the current drawn by a semi-converter from a sinusoidal AC voltage source is shown in the figure. If I0 is equal to 20 amperes, the RMS value of the fundamental component of the current is dash amperes. To know the concept of single phase controlled rectifiers, audience can go through the given NPTEL video link. Let us discuss some useful information to solve the problem. Here, any periodic non-sinusoidal waveform of the time period C to C plus 2L can be expressed using this Fourier series expression. So, that is f of x is equal to a0 by 2 plus summation of all harmonics into an cos n pi x by L plus bn sin n pi x by L, where a0 is equal to 1 by L integral c to c plus 2L f of x dx and an is equal to 1 by L integral c to c plus 2L f of x cos n pi x by L into dx and bn is equal to 1 by L integral c to c plus 2L f of x sin n pi x by L. Here a0 is the DC component of the waveform, whereas an is the even component of the waveform and bn is the odd component of the waveform. Using this information, let us solve the problem. First, given data. What it is given? This magnitude of I0, they have told it as 20 amperes. And this is the waveform of the current drawn by a semi-converter. So, we need to find out the fundamental RMS component of the current. This thing we need to find out. So, we know that any waveform, anything can be expressed as DC component plus sinusoidal component, means all harmonics will come, all sinusoidal harmonics plus all even harmonics. Any waveform we can express using Fourier series. This is odd harmonics. Any waveform we can express like this. So, from the diagram we can say that whatever the positive half cycle, the similar waveform is repeated for the negative half cycle. So, this DC component of the waveform is 0, since positive half cycle is nullifying the negative half cycle. So, we don't have to calculate the DC component. So, A0 is equal to 0. Now, come to the odd harmonics. See, odd waveform means f of x is equal to minus f of x. F of minus x is equal to minus f of x. This is the odd waveform. So, let us analyze whether this waveform is odd waveform or not. Waveform is given like this, right? This thing we can say f of x. This is x, this is f of x. So, if we expand the waveform in the negative direction, this will come like this, right? This is f of minus x. But if we invert this f of x, we will draw just to the next level. It is coming like this, right? Like this. We need to follow the pattern. So f of x is exactly the inversion of this is x, this is f of minus x. So from these two diagrams we can say f of x is equal to minus f of x. So this is odd waveform. Odd waveform, right? So it will have odd harmonics. We need to calculate this thing. Now let us see whether the waveform is even or not. Even waveform means f of minus x is equal to f of x. This is even waveform. Anyway, from this diagram itself we can say that there is no even component here. So this even component is 0 because f of x here in this waveform f of x minus x is not equal to f of x. So even component is 0. So we just have to calculate the odd harmonics. So I naught of t is equal to summation of n equal to 1, 3, 5 till infinity. Any kind of waveform, like if it follows the similar pattern with magnitude I naught, that magnitude will be 4 I naught by n pi. This is the magnitude. Into depends on the firing angle alpha, the component will vary, right? So and this is that component depends on alpha, so cos n alpha by 2, and it is only cos nature. Into it will have odd harmonics, right? So into sin n omega t minus n alpha by 2. So this is the I naught. This component is due to the magnitude and this component is due to the firing angle, and this is odd harmonic. So sin n omega t minus n alpha by 2. So whenever you solve the problem, if the similar pattern comes means you just have to follow this similar expression. So in the question it is asked to find out the RMS and fundamental component, RMS of the fundamental component. RMS value means first we will find out the RMS value. IN RMS is 4 I naught by n pi into cos n alpha by 2. This is the magnitude of the maximum component divided by root 2. This is the IN RMS. So I1 RMS means n is equal to 1. So 4 I naught by pi into cos alpha by 2 into root 2. In the question alpha it is given that 30 degrees, right? So 2 root 2 by pi into cos 30 by 2 15 degrees. If we simplify this thing, we will get this thing as 17.39 amps. So, the fundamental RMS component of the current is 17.39 amps. So, the RMS value of the fundamental component of the current is 17.39 amps. Thank you.